On the 22nd of July, 2025, in the city of Fuzhou, Fujian province, a groundbreaking workshop on advanced nuclear energy marked a pivotal milestone for China. The China National Nuclear Corporation, or CNNC, proudly announced the completion of the preliminary design for the world's first fourth-generation commercial fast reactor, named the CFR-1000, boasting a power capacity capable of supplying electricity to a major city like Houston. The CFR-1000 promises to deliver a stable, clean, and cost-efficient energy source, meeting the ever-growing demands of modern urban centers. This landmark event also sends a powerful message about the rapid pace of China's technological advancements. While many nations are still conducting research on fourth-generation technologies in laboratory settings, China has boldly advanced to the commercial design phase. This achievement is not only a source of immense pride for China, but also a stark reminder of the shifting balance in global technological innovation. In a world urgently seeking solutions to combat climate change, the CFR-1000 stands as a bold declaration that China is not merely participating in the race, but is leading the charge. Join Top 10 Discoveries Official as we dive deep into the fascinating story of the CFR-1000 fourth-generation commercial fast reactor, exploring the technological breakthroughs and strategic vision behind China's ambitious leap forward. Unlike traditional thermal reactors, which rely on slow neutrons to sustain fission reactions, fast reactors operate using fast neutrons, high-energy particles that enable far more efficient fission. The result is a groundbreaking leap. Fast reactors can harness up to 95% of the energy from uranium fuel, compared to just 5% in conventional thermal reactors. This means that 1 ton of uranium, sufficient to power a city like Seattle in the United States for 1 year, can be reused to generate energy for dozens of years more. Fast reactors, such as the CFR-1000, are classified as fourth-generation technology, the most advanced tier of nuclear energy. They are designed with 3 core objectives: safety, sustainability, and economic efficiency. In terms of safety, fast reactors employ liquid sodium cooling systems, which naturally dissipate excess heat without requiring complex pump systems. This reduces the risk of severe accidents, such as reactor meltdowns, to nearly zero. A specific example: sodium-cooled reactors can automatically halt reactions if temperatures rise too high, a feature that third-generation reactors, like the AP-1000 used in the United States, cannot yet match. Regarding sustainability, fast reactors usher in a new era for nuclear fuel management. They can recycle used fuel, transforming radioactive waste, which typically requires thousands of years to decay, into new fuel sources, while reducing waste storage time to just a few hundred years. This not only decreases the volume of waste, but also addresses one of the greatest challenges in the nuclear energy industry: long-term waste disposal. With a reactor like the CFR-1000, radioactive waste can be reduced by up to 80% compared to traditional reactors, an impressive figure when considering environmental impact. Economic efficiency is another standout strength. Fast reactors cut fuel costs by up to 35% through recycling capabilities, while producing electricity at a competitive rate of approximately 4 cents per kilowatt-hour, lower than the 6 cents of third-generation reactors. With a capacity of 1,200 megawatts, a single CFR-1000 reactor can supply electricity to over 1.5 million households, equivalent to the entire population of Philadelphia in the United States, without relying on fossil fuels like coal or natural gas. Moreover, this technology offers superior stability compared to solar or wind energy, which are subject to weather fluctuations. The significance of fast reactors is further reinforced by global operational experience. With over 400 years of sodium-cooled reactor operations worldwide, from Russia to Japan, this technology has proven its reliability and efficiency. China's CFR-1000 not only builds on these foundations, but also integrates modern innovations to optimize performance. This is why fast reactors are seen as the key to meeting the world's growing energy demands, particularly as climate change drives nations to seek cleaner, more reliable energy sources. As the world grapples with the challenge of powering large urban centers without harming the environment, fast reactors like the CFR-1000 emerge as a revolutionary solution. They not only provide electricity, but also lay the foundation for a sustainable energy economy, from power generation to new industrial applications. With China leading the way, this technology is opening a new chapter for nuclear energy, promising to transform how we envision the future of energy. The journey to position China as a global leader in fast reactor technology is a remarkable tale of ambition, perseverance, and astonishing development speed. In less than 2 decades, this nation has progressed from a modest experimental reactor to designing a large-scale commercial fast reactor named the CFR-1000. This path unfolded through 3 distinct phases: the experimental CEFR reactor, the demonstration CFR-600 reactor, and the pinnacle, the commercial CFR-1000 reactor with a capacity of 1,200 megawatts, sufficient to power a city like San Diego in the United States. The journey began in 2011 with the China Experimental Fast Reactor, or CEFR, at the China Institute of Atomic Energy near Beijing, with a modest capacity of 20 megawatts. The CEFR marked China's initial step toward mastering fast reactor technology. This reactor achieved criticality in 2010 and was officially connected to the national power grid 1 year later. By 2020, the CEFR successfully passed an emergency shutdown test at maximum capacity, proving the safety and stability of its design. The success of the CEFR extended beyond its operation, as it laid the foundation for a domestic supply chain, with over 70% of components manufactured locally. This was a critical advancement, enabling China to reduce reliance on foreign technology and establish a platform for larger projects. The next phase was the CFR-600 demonstration reactor, a significant leap in scale and ambition. Construction began in December 2017 in Jiapu County, Fujian Province, on Changbiao Island, with the CFR-600 boasting a capacity of 600 megawatts, 30 times that of the CEFR. This reactor commenced commercial operation in 2023, marking China's first large-scale practical application of fast reactor technology. A second CFR-600 reactor was also initiated at the same site in 2020, showcasing rapid deployment. The CFR-600 uses MOX fuel, a mixture of uranium and plutonium oxides, initially supplied by Russia but later produced domestically at a recycling facility in Fuzhou. Capable of generating electricity for over 700,000 households, the CFR-600 demonstrated that China was not merely experimenting, but was ready for commercial projects. The CFR-1000 represents the pinnacle of this trajectory. Announced as having completed its preliminary design in July 2025, this reactor doubles the capacity of the CFR-600, reaching 1,200 megawatts, scheduled to begin construction in 2028 and enter commercial operation in 2034. The CFR-1000 is a testament to China's technological self-reliance. The nation has now localized over 85% of components and technology, from reactor design and liquid sodium cooling systems to advanced monitoring sensors. Remarkably, China has built a complete nuclear industry chain in record time, while many other nations struggle with experimental projects. This rapid pace of development sets China apart. While fast reactor projects in the United States, such as the Natrium reactor with a capacity of only 345 megawatts, remain in the research phase, China has advanced to commercialization. From the CEFR to the CFR-1000, this journey showcases not only technical prowess, but also strategic vision, transforming China from a learner to a leader. With each milestone, China is reshaping how the world perceives nuclear energy, ushering in a new era of clean and sustainable energy. China's CFR-1000 commercial fast reactor stands out not only for its scale, but also for its cutting-edge technologies, making it one of the most advanced nuclear designs in the world. With a capacity of 1,200 megawatts, sufficient to power over 1.5 million households, equivalent to the entire population of Dallas in the United States, the CFR-1000 integrates technical innovations that surpass previous reactor generations. This represents a breakthrough, not only in performance, but also in safety and fuel recycling capabilities, solidifying China's leadership in fourth-generation nuclear energy technology. A standout feature of the CFR-1000 is its liquid sodium cooling system, an advanced technology ensuring stable and safe operation under all conditions. Unlike traditional thermal reactors that use water as a coolant, liquid sodium has a higher boiling point, reaching up to 1,600 degrees Fahrenheit, allowing the reactor to operate at high temperatures without requiring significant pressure. This reduces the risk of accidents due to leaks or explosions, issues that plague second-generation reactors. The CFR-1000's passive cooling system further enables the reactor to automatically dissipate excess heat without mechanical pumps, virtually eliminating the risk of a meltdown, a superior safety feature compared to older designs like the Fukushima reactors. The CFR-1000 employs MOX fuel, a mixture of uranium and plutonium oxides, in its initial phase, with plans to transition to U-0 metallic fuel in the future. This metallic fuel enables a high-energy burnup rate, up to 150 gigawatt-days per ton, 3 times that of conventional uranium fuel. As a result, the reactor can utilize up to 95% of the fuel's energy. Compared to just 5% in traditional thermal reactors, this not only boosts efficiency, but also significantly reduces the amount of fuel needed, saving millions of United States dollars annually in operating costs. A single CFR-1000 reactor can generate electricity continuously for 60 years, with maintenance costs 20% lower than those of third-generation reactors. Another highlight is the intelligent control system integrated with artificial intelligence. The CFR-1000 uses advanced sensors to monitor temperature, pressure, and neutron flux in real time. AI algorithms analyze this data to optimize reactor performance, predict potential issues, and automatically adjust operations to maintain safety. For instance, if the reactor's temperature rises abnormally, the system can reduce fission reactions within seconds, preventing risks without human intervention. This technology enables the CFR-1000 to achieve a reliability rate exceeding 98%, an impressive figure in the nuclear energy industry. Compared to other fast reactor projects worldwide, the CFR-1000 stands out for its scale and technological integration. While the Natrium reactor in the United States, with a capacity of 345 megawatts, remains in the testing phase with no clear commercialization timeline, the CFR-1000 is designed for mass production. The reactor's design complies with the strictest international safety standards set by the International Atomic Energy Agency, IAEA, ensuring stable operation in any country. Moreover, China has optimized the manufacturing process to reduce construction costs to approximately 3.5 billion United States dollars, 15% lower than the average cost of third-generation reactors. The CFR-1000 is not just a technical marvel, but also a symbol of China's innovation. By combining safety, efficiency, and advanced technology, this reactor sets a new standard for the global nuclear energy industry. It not only provides electricity, but also unlocks potential for future clean energy applications, from hydrogen production to industrial heat supply, bringing China closer to its goal of reshaping how the world uses energy. With a capacity of 1,200 megawatts, sufficient to power over 1.5 million households, equivalent to the entire population of Phoenix in the United States, the CFR-1000 delivers exceptional benefits in economics, energy security, and environmental protection. It marks a significant step in China's strategy to build a clean energy economy, reduce reliance on fossil fuels, and achieve its carbon neutrality goal by 2060. Economically, the CFR-1000 is designed to optimize electricity production costs, bringing the price down to just 4 cents per kilowatt hour, significantly lower than the 6 cents of third-generation reactors. Its nuclear fuel recycling capability reduces fuel costs by 35%, saving hundreds of millions of United States dollars annually over the reactor's 60-year lifespan. This is particularly vital for China, a nation with rapidly growing energy demands, where over 300 million households and industries consume electricity equivalent to 7,500 billion kilowatt-hours annually. By deploying reactors like the CFR-1000, China can provide affordable and stable electricity, driving economic growth without compromising the environment. Energy security is a core strategic benefit of the CFR-1000. With its ability to recycle fuel, this reactor utilizes up to 95% of uranium. Compared to just 5% in traditional thermal reactors, this reduces China's dependence on imported uranium, which accounted for 70% of its supply in 2020. Instead of importing thousands of tons of uranium annually from countries like Australia or Canada, China can reuse processed fuel, creating a closed fuel cycle. This not only enhances self-reliance, but also shields the economy from global energy market fluctuations. A single CFR-1000 reactor can operate continuously with only 1/10 the initial fuel required by traditional reactors, ensuring long-term energy stability. Environmentally, the CFR-1000 is a major leap in reducing greenhouse gas emissions. One such reactor can cut 10 million tons of carbon dioxide annually compared to a coal plant of equivalent capacity, equivalent to removing 2 million cars from the roads each year. With over 55% of China's electricity still derived from coal in 2025, deploying reactors like the CFR-1000 helps phase out polluting energy sources. Additionally, its ability to reduce radioactive waste volume by 80% compared to traditional reactors addresses a major challenge in the nuclear energy industry. Waste from the CFR-1000 requires storage for only a few hundred years, rather than thousands, easing the burden on future generations. Compared to global efforts, China is a step ahead with the CFR-1000. While the United States focuses on smaller experimental projects like the Natrium reactor, with a capacity of only 345 megawatts, China is poised for large-scale commercialization, with 27 nuclear reactors under construction, accounting for nearly 40% of new reactors globally. China is not only meeting domestic needs, but also laying the groundwork for exporting nuclear technology. The CFR-1000 symbolizes this ambition, delivering clean energy while reinforcing China's role as a global innovator in the fight against climate change. The benefits of the CFR-1000 extend beyond electricity production. It is part of China's long-term strategy to build a sustainable energy ecosystem, from powering major cities to supporting new industries. With its cost savings, enhanced energy security, and environmental protection, the CFR-1000 is more than a reactor. It is a bold statement that China is leading the way in shaping the world's clean energy future. In a world yearning for sustainable energy solutions, China's CFR-1000 commercial fast reactor goes beyond mere electricity production. The CFR-1000 unlocks a range of groundbreaking applications, from green hydrogen production to seawater desalination and providing heat for heavy industries. These applications not only meet energy demands, but also reshape new industries, cementing China's pioneering role in building a clean and diverse energy economy. One of the most promising applications of the CFR-1000 is green hydrogen production, a clean fuel seen as key to replacing fossil fuels in transportation and industry. Thanks to its ability to generate stable high temperatures, the CFR-1000 can power high-efficiency electrolysis processes, producing hydrogen at a cost 30% lower than methods using solar or wind energy. A single CFR-1000 reactor can produce up to 500,000 tons of hydrogen annually, enough to fuel over 2 million fuel cell vehicles, equivalent to the entire vehicle population in the San Francisco Bay Area in the United States. This significantly reduces carbon emissions from transportation, a sector accounting for nearly 30% of carbon dioxide emissions in major urban centers. Additionally, the CFR-1000 has the potential to revolutionize seawater desalination, a critical solution to global freshwater shortages. With its abundant thermal and electrical energy, one CFR-1000 reactor can power desalination plants, producing up to 100 million gallons of fresh water daily, sufficient to meet the needs of a city like Miami in the United States. China, with over 11,000 miles of coastline and growing freshwater demands, has begun testing nuclear-powered desalination at facilities in Hainan. This success not only serves domestic needs, but also opens opportunities to export clean water solutions to arid regions like the Middle East. Another application of the CFR-1000 is providing industrial heat for heavy manufacturing sectors such as steel, cement, and chemicals. These industries, which consume up to 25% of China's total energy, typically rely on coal, generating billions of tons of carbon dioxide annually. The high temperatures from the CFR-1000 can replace coal in smelting furnaces, reducing greenhouse gas emissions by up to 40% per ton of steel produced. For example, a typical steel plant using heat from the CFR-1000 could save $50 million in fuel costs annually, while cutting 1 million tons of carbon dioxide, equivalent to planting 15 million trees. China has tested this application with the high-temperature HTR-PM reactor in Shandong, and the CFR-1000 is expected to scale it up. These applications are not just concepts but are being implemented by China. With its ability to integrate into diverse industries, the CFR-1000 is transforming nuclear energy into a versatile platform, not limited to electricity production. Compared to other nuclear projects worldwide, such as the Natrium reactor in the United States with a capacity of 345 megawatts, the CFR-1000 excels in scale and applicability. While other nations are still researching similar solutions, China has laid the foundation to bring this technology to reality, from coastal cities to industrial hubs. The potential applications of the CFR-1000 not only address energy challenges, but also create new economic opportunities. By leading in hydrogen production, desalination, and industrial heat, China is building a clean energy ecosystem, positioning itself at the forefront of the global innovation race. The CFR-1000 is more than a reactor. It is a vision for the future, where nuclear energy drives sustainable industries, from transportation to manufacturing, and from clean water to environmental protection. When China unveiled the CFR-1000 commercial fast reactor, it did more than introduce a new technology. It outlined a daring vision for the future of global energy. With the potential to reshape the energy sector, the CFR-1000 serves as the cornerstone of China's long-term plan to lead in fourth-generation nuclear energy. From scaling up domestically to exporting technology worldwide, China is transforming nuclear energy into a driver of economic growth and environmental sustainability, setting a new benchmark for other nations. China's long-term vision is to make fast reactors like the CFR-1000 the backbone of its national energy system. By 2050, China aims to achieve 200,000 megawatts from fast reactors, enough to power over 250 million households, equivalent to the entire population of the United States. This would account for approximately 15% of China's total electricity production, significantly reducing reliance on coal, which still supplies over 50% of the nation's electricity in 2025. With plans to deploy multiple CFR-1000 reactors starting in 2034, China expects to build at least 20 such reactors over the next 2 decades, with an estimated total investment of $70 billion United States dollars. This not only strengthens energy security but also boosts related industries, from component manufacturing to engineer training. Technology export is a critical component of China's strategy. Through the Belt and Road Initiative, China is negotiating to bring fast reactor technology to countries like Pakistan and Argentina. A notable example is the Memorandum of Understanding signed with Argentina in 2024 to develop fast reactors in South America. These agreements not only generate billions of United States dollars in revenue, but also expand China's influence in global clean energy. With over 60 countries participating in the Belt and Road Initiative, technologies like the CFR-1000 could become an international standard, directly competing with Western energy solutions. Technological innovation is central to this vision. China is integrating artificial intelligence and Internet of Things technology into the operation of the CFR-1000, reducing maintenance costs by 10% through automated monitoring and predictive systems. For instance, Internet of Things sensors can detect the slightest changes in reactor operations, from pressure to temperature, enabling real-time adjustments to optimize performance. China is also researching next-generation fast reactors with capacities up to 2,000 megawatts, promising even greater economic and environmental benefits. These advancements position China at the forefront, far ahead of experimental projects like the 345-megawatt Natrium reactor in the United States. However, China faces challenges in ensuring transparency, particularly in plutonium recycling, a key part of the closed fuel cycle. To meet international standards, China is collaborating with the International Atomic Energy Agency to enhance oversight and information sharing, addressing global concerns. By tackling this challenge, China can solidify its reputation as a reliable technology provider, opening doors to broader international cooperation. China's vision for the CFR-1000 extends beyond electricity production to building a comprehensive energy ecosystem. From powering major cities with clean energy to supporting new industries like hydrogen production and desalination. The CFR-1000 is a strategic step toward redefining global energy use. With long-term planning and robust investment, China is sending a clear message. Fourth-generation nuclear energy is not just the future, but the present, and they are leading the way. In a world grappling with the dual challenge of surging energy demands and a climate crisis, China's CFR-1000 commercial fast reactor emerges as a groundbreaking solution, reshaping the future of clean energy. With a capacity of 1,200 megawatts, this reactor is not merely a technological achievement, but a testament to China's strategic vision, transforming nuclear energy into a catalyst for sustainable development. The journey from initial steps to an advanced commercial design demonstrates that China is not just participating, but leading the global energy revolution. The CFR-1000 represents a turning point in how we perceive nuclear energy. It is not just a power source, but a versatile platform, unlocking potential for new industries and addressing major 21st century challenges. Its ability to recycle fuel, reduce radioactive waste, and produce affordable energy has positioned China at the forefront, surpassing experimental efforts in other nations. While the world debates the future of clean energy, China has taken action, turning vision into reality with remarkable speed and scale. What sets the CFR-1000 apart? It integrates critical elements: safety, efficiency, and sustainability to create a comprehensive energy model. With low electricity production costs and the capacity to support applications from hydrogen production to seawater desalination, this reactor not only meets domestic needs, but also lays the foundation for global influence. China is leveraging the CFR-1000 to shape an energy ecosystem where major cities, heavy industries, and even other nations can benefit from this technology. Cooperation agreements with countries like Argentina and Pakistan are evidence that China is not just building reactors, but exporting a new energy future. The success of the CFR-1000 serves as a powerful reminder of the strength of strategic innovation. In less than 2 decades, China has built a complete nuclear industry chain, achieving over 85% self-reliance in technology and components. This not only bolsters its economic standing, but also solidifies its leadership in the race for clean energy. As other nations strive to balance growth and environmental protection, China has set a new standard, proving that nuclear energy can address both objectives. Looking ahead, the CFR-1000 is not just a milestone, but a lesson for the world to rethink energy challenges. Can other global powers, such as the United States or Russia, learn from China's speed and ambition to accelerate their energy transitions? Could fourth-generation nuclear energy become the foundation for a carbon-free world? Share your thoughts in the comments below. Don't forget to hit subscribe to stay updated on the latest analyses of technology, national strategies, and innovations shaping the future. Top 10 Discoveries Official will be back with untold stories, projects that push boundaries, and quiet revolutions with global impact. See you in the next video.